In this lesson, we're going to talk about resistance. Now, resistance is a device, a resistor is a device that limits the flow of current through a circuit. Ideally, electric wires, like the high power wires we get our electricity from, that delivers it to our house, should be superconductors, i.e. they should be conductors that have zero resistance to the flow of electricity. Now they don't. Most wires that we have in our house have a very small resistance value. They're not superconductors, although there are some materials that at very low temperatures do indeed have zero resistance to the flow of electricity. We're going to pretend, for the purposes of this class, that the wires in a circuit that don't have any circuit element directly attached, like capacitors or resistors or inductors, which we'll talk about later, those wires are superconductors, that they have zero resistance to the flow of electricity. So a resistor is a device that is made up of a conductor that limits the flow of electricity. So it is metal, typically copper, aluminum, where electricity is free to flow, but it is designed in such a way that it slows the flow of electricity. It pushes back against the flow of electricity. Imagine, in a plumbing example, a large hose going to a small hose. That smaller hose restricts the flow of water, so it provides resistance to the flow of water. So a smaller hose would be a resistor in that example. This is electricity, of course. So resistors have very specific values depending on how much you want to restrict the flow of electricity. So the resistance is a property of resistors. The symbol for a resistor in an electric circuit is just basically this sawtooth pattern. So again, this jagged line up and down, up and down, up and down. As a reminder, the SI unit for resistance is called the ohm. The ohm is represented by the symbol, Greek symbol omega, instead of 0, right, or O. Most units, like the watt is a W, the joule is a J, the meter is an M. Ohm can't be an O because it looks too much like a 0. So physicists use the Greek letter omega to represent ohms. And a very simple circuit drawn here as an example of what a resistor looks like in a circuit. So we have a battery here, uneven parallel lines. The longer line is the positive terminal of the battery, the shorter line is the negative terminal. Connected, again, these we pretend are superconductors. There's zero resistance to the flow of electricity in these simple conducting wires. That's not exactly true, but for the purposes of this class, we can pretend it is. As the battery, when you connect the terminals of the battery, current flows from the positive terminal to the negative terminal. That's shown here by the direction arrows and the current I. And that current crosses the resistor R. So here's that sawtooth pattern, but here vertically rather than horizontally, showing that this circuit has a resistor in it. Now, like capacitors, resistors can be combined in series and parallel to give you just different resistance values. Like, for example, let's say I need a 10 ohm resistor in this circuit for it to work or it to do what I want it to do. What happens if I don't have a 10 ohm resistor? Well, we can combine resistance values we do have in order to replicate a 10 ohm resistor. So let's look at what happens when we combine resistors in a series configuration and in a parallel configuration. When combining resistors in series, we have to remember what a series configuration is so we can identify it. And a series configuration is a configuration where you have to go through the second circuit element if you go through the first circuit element. So for example, I have current flowing down this wire to the right, so some current I flowing in this wire. That current has to go through resistor 1, it doesn't have a choice. It has to go through resistor 2, it has to go through resistor 3, and it has to go through resistor 4 and come out the other side, right? It doesn't have a choice in the matter. It has to go through all 4 of those circuit elements. So those circuit elements we say are in series. Now, if we want to look at what it would look like in an actual circuit, here's a very simple circuit with, instead of 4 resistors, I have 3 drawn here. So you have a battery connected through 3 resistors. So current will flow from the positive to the negative terminal of the battery, right? In a clockwise fashion through this circuit, current will flow through all 3 resistors. It must go through all 3 resistors. It must go through resistor 1, and then resistor 2, and then resistor 3. It doesn't have a choice. But rather than having 3 resistors in this configuration, wouldn't it be nicer if we could simplify the circuit into one where we just have a single resistor? Now again, like capacitors, we discussed this with capacitors, the opposite is usually the way we go. We see that we need a very specific resistance value for a circuit. We don't have that exact resistance value, but we can combine the resistors we do have in such a way where we replicate that resistance value. Well, how do we simplify resistors in series? Well, to combine resistors in series, you simply add up the individual resistance values of each circuit element that's in series, right? So, resistance value, R sub S, resistance value in series, this resistor value is just the algebraic sum of these 3 resistors. Now, resistances can't be negative, they have to be positive. So for example, maybe we don't have a 20 ohm resistor, but we have a 10 ohm and 2 5 ohm resistors. So 10 plus 5 plus 5 is 20. So I can replicate, these 2 circuits are identical. I can replicate this circuit with a 20 ohm resistor using 2 10s, or 10 and 2 5s, or a 15 and 2 2.5s, or whatever. I can replicate the resistance value that's required by using resistors that are known. Now note, and this is an important distinction, this is the opposite of when we talked about capacitors. When we talked about capacitors in parallel, we simply added the capacitance values together. Now we're doing this, we're simply algebraically adding the resistance values together for resistors in series. So, see how they're flipped. Capacitors in parallel are simply added together. Resistors in series are simply added together. Now capacitors in series, it was the reciprocal of the sum of the reciprocals of the capacitance values. Resistance values in parallel we'll see is the reciprocal of the sum of the reciprocal of the resistance values. And we'll look at that next. When we look at resistors in parallel, we have to remember what a parallel configuration is. So I have a parallel configuration drawn here in black. The battery, again, has some voltage or EMF across the terminals of the battery, 9 volts, 12 volts, whatever. Now the current has the option of either going through resistor 1, we'll call that current I1, through resistor 1. We have current I2 through resistor 2, and we have current I3 through resistor 3, right? So if you leave the positive terminal of the battery, to get back to the negative terminal, you have 3 options that take you back to the negative terminal of the battery. The analogy would be, again, imagine going to a store with multiple checkout lanes. You can go through checkout lane 1 or checkout lane 2 or checkout lane 3, assuming they're open, and leave the store. You don't have to go through checkout lane 1 and then 2, right? You don't have to go through multiple checkout lanes. You can choose which one you go through, and then you're back to where you started from. So that's a parallel configuration. And again, a parallel configuration, I have 3 resistors shown here. I would like to simplify the circuit, so I have a single resistor. What resistance value do I need that will replicate the resistance value of these 3 resistors in parallel? Well, we talked about it a little bit earlier, right? It's the reciprocal of the sum of the reciprocals of the individual resistance values. So if I have 3 resistors in parallel here, it's 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 plus 1 over 4, 1 over 5, 1 over 6 if I have multiple resistors in parallel. If I only have 2, then it's just 1 over R1 plus 1 over R2. But remember, that's equal to the reciprocal of the resistance in parallel. So R sub P means the equivalent resistance for a parallel configuration. It's not equal to the resistance in parallel is not equal to 1 over R1 plus 1 over R2, the reciprocal of the resistance value. So let's say each of these resistors is 10 ohms, right? So this problem would become, let's do it in green. This problem would become, it's equal to 1 over 10 ohms plus 1 over 10 ohms plus 1 over 10 ohms, which is equal to, it's not 3 over 30. A lot of people forget how to add and subtract fractions at this point in their careers after they've had geometry and algebra. You forget basic middle school, elementary school math. These already have a common denominator, so you can add them together. So it's 3 over 10 ohms. So you're like, oh, it's 1/3, right? 3 divided by 10 is 1/3, or 0.33 if you're repeating. But it's 1 over RP. So RP, in this case, would be equal to the inverse of this, which is 10 ohms over 3, or 3.3 ohms. So if I have 3 10 ohm resistors, I can replace them in parallel configuration. I can replace them with a single 3.333 ohm resistor that does the same job. Okay, so that's when you add resistors in parallel. The problem is circuit elements can actually be quite complicated. Usually resistors are set up in circuits in such a way where you're not sure if they're in a parallel configuration or a series configuration, and sometimes they're not either. They're neither parallel or series. Let's look at the example your book gives, this black circuit I have drawn here. So we have a battery, there's a resistor here, 3 resistors located here, 2 resistors located there. So we have a total of 1, 2, 3, 4, 5, 6, 7 resistors in this circuit. No one equation is going to allow me to simplify this circuit down to a single resistor. I have to take this circuit and break it down step by step by step, identifying resistors that are in series with one another and identifying resistors that are in parallel with one another, and then simplifying those resistors, redrawing the circuit, and then again identifying resistors that are in series or parallel. For instance, these 2 resistors, you might be tempted to say, oh, these are in series, because you go through the top resistor and then you can go through the resistor down here. That's not accurate, because if you go through this first resistor, the current has a choice of either going through this complicated set of resistors or down. It's not forced to go through the second resistor here if it goes through the first resistor. It has an option. So these 2 circuit elements are not in series. Well, what circuit elements are in what? Well, I've drawn red dotted lines around the circuit elements that are in parallel. Again, parallel means you can choose multiple paths to get back to the same point. So here, if I'm on this path, the current has a choice of going through this top resistor, this middle resistor, or this bottom resistor to get back to the same point. So these 3 resistors are in parallel. Likewise, over here, the current can either go through resistor on the right, or it can go through the resistor on the left to get back to the same point. Therefore, these 2 resistors are in parallel. Note, they're not in parallel with one another. So what you have to do in this situation, combine these 3 resistors into a single resistor using the equation here, depending on what the resistance values of those resistors are, and combine these 2 resistors in parallel into a single resistor. Once you know what these resistance values are, you redraw the circuit and you reanalyze it. Okay, now, do I have resistors that might be in series? Do I have resistors that might be parallel? Well, these 2 resistors shown in blue now, circled in blue, are in series, because you can see if you go through resistor 1, you must go through resistor 2, right? You don't have a choice. There's only one path connecting these 2 resistors, so they're in series. So combining these resistors in series into a single resistor value, simplifying the circuit, now looking, okay, which one of these resistors are in series, which one are in parallel. Well, now these two resistors are in parallel with one another. Use this equation here to combine them into a single resistor. Redraw the circuit. Now you have two resistors that are in series. Use the previous equation to combine those down to a single resistor. So you can see that there are a lot of steps here, right? We had to use these equations 1, 2, 3, 4, 5 times to get to our final circuit element. And sometimes resistors are neither in series nor in parallel. Now you have to be careful, again, what we mean by series and parallel. The problems in your book are usually set up that they are, because we're not throwing incredibly complex problems at you. However, be careful about your analysis of resistors. Make sure you know what a series configuration is for resistors and capacitors, or any circuit element. Make sure you know what a parallel configuration is, and we will look at more complicated circuits a bit later.